we want to look at the molar mass for gases and how we can calculate those values. So we can use PV equals nRT to solve for our molar mass of a gas using density. So let's do some algebra. Let's start with PV equals nRT. And our molar mass equals the mass in grams divided by moles, grams per mole. Now we're going to play around with this a little bit. We're going to multiply both sides by n and divide both sides by molar mass. And that gives us n equals m over mm. So the number of moles of gas equals the mass of that gas divided by its molar mass. Now we're going to do a substitution. For n in our ideal gas law problem, we're going to substitute in m over mm. So PV equals mRT over mm. And then we're going to play a little bit more algebra. We're going to multiply both sides by molar mass and divide both sides by PV. And we're going to get our molar mass equals mRT over PV. So if we know the mass of a gas and the temperature, pressure, and volume for that gas, we can calculate its molar mass in grams per mole. Now, one other thing we can do. If we have mass divided by volume, that gives us density. So we could substitute in for m divided by v for d. So molar mass equals dRT over P. And this is a way that we can calculate the molar mass of a gas. So we'll look at a problem. A gas at 34 degrees Celsius and 1.75 atm has a density of 3.4 grams per liter. Calculate the molar mass of the gas. All right, so we're given a density and we want to calculate the molar mass. So molar mass equals dRT over P. So for the density, we'll plug in 3.4 grams per liter. For R, since our pressure is in atm, 0.0821 atm liter per mole Kelvin. And we'll change our temperature from Celsius to Kelvin by adding 273, and that'll give us 307. We'll divide that by our pressure, which is 1.75 atm. Now when we look at that, atm is going to cancel out, liters is going to cancel out, Kelvin is going to cancel out, and we're going to be left with grams per mole, and that's what we're trying to find. So the molar mass for this gas is 49 grams per mole. Now let's talk about the law of partial pressures. And when we deal with the law of partial pressures, what we're looking at is instead of just one gas in a container, we're looking at a mixture of gases in a container. And the total pressure exerted by that mixture is the sum of the pressures that each of the gases would exert alone. So if we look over here, if we have a gas in this container that has a pressure of, let's say, 1 atmosphere, and we have a second container that, or two, let's say 2 atmospheres, since we've got 2 masses up here. And the mass, or the pressure in our second container is 1, 2, 3, 4, 5. If we were to mix these 2 gases together in the same volume, our total pressure is going to be 2 plus 5, or 7. 1, 2, 3, 4, 5, 6, 7. So what that's telling us is P total equals P for gas 1 plus P for gas 2, and so forth, depending on how many gases we have in the particular container. When we look at N total, we're looking at the number of moles total in a container. And for a mixture of gases, it's the number of total moles that are present in a container that determine the pressure not what the gas particles actually are. So we're going to look at a problem. And again, we're going to look at the problem here and then we're going to solve it on the next page. So it says mixtures of helium and oxygen are used in scuba diving tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees Celsius and 1 atm and 12 liters of oxygen at 25 degrees Celsius and 1 atm were pumped into a tank with a volume of 5.0 liters. Calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees Celsius. All right, so let's look at our problem. We're going to first start with helium. And it gave us the pressure, volume, and temperature for our helium gas originally, so we can find out how many moles of gas we have. PV equals nRT. We've got 1.0 atm, 46 liters. We want to find out how many moles. 0.0821 atm liter per mole Kelvin. And we'll change our temperature from Celsius to Kelvin, and that would give us 298 Kelvin. So when we solve for n equals 1.88 moles of helium. We're going to do the same thing for our oxygen. PV equals nRT. So for our oxygen, we have 1.0 atm, 12 liters. We don't know how much. 0.0821 atm liter per mole Kelvin. And we'll add 73 to our temperature to get Kelvin, so that'll give us 298 Kelvin. So we'll get 0.49 moles of oxygen gas. Well, it's the total number of moles of gas that are going to help us to determine what the total pressure is. So we're going to take 1.88 plus 0.49 and get our total number of moles. So 1.88 plus 0.49 gives us 2.37 total moles of gas. And again, it's not the identity of the gas, it's how many moles we have that are important. Now we can find out what the total pressure exerted by this container is. So PV equals nRT. We want to find out what the total pressure is. The new volume of the container is 5 liters. The total number of moles of gas is 2.37. We'll use 0.0821 for our R value. And our temperature is 298. So that's going to give us a total pressure of 11.6 atm in this new 5-liter container. Now, each of the gases is going to exert part of that total pressure. So what we're going to figure out now is what part of the whole are each of the gases in terms of moles, and then we'll be able to figure out what part of the whole in terms of pressures. So what we're going to look at is what's called our mole fraction for helium. And it's just going to be the moles of helium over the total. So 1.88 over 2.37 is going to give us 0.793. And we're going to leave it as a decimal, even though it's called a mole fraction. We're going to leave it as a decimal. It really means that the helium is 79.3% of the total gas. And our mole fraction for oxygen will be the part over the whole for oxygen. So 0.49 over 2.37, which will give us 0.207, or 20.7%. We can check our answer because it should add up to 1, or if we change them to percents, it would add up to 100%, and it does. So if we want to find out now what the partial pressure of the helium is, it would be the total pressure exerted by the mixture, so 11.6 atm times the mole fraction, 0.793. And that's going to give us 9.20 atm as our partial pressure for the helium. Our partial pressure for the oxygen will be determined by taking the total pressure exerted by the mixture, so 11.6 atm, times the mole fraction for oxygen, 0.207. And that'll give us a partial pressure for oxygen of 2.40 atm. And again, we can kind of double check our answer because the partial pressure of helium plus the partial pressure of oxygen should give us the total pressure exerted by the mixture. And 9.20 plus 2.40 gives us 11.6.